Happy Halloween! Honestly, it may not even be close to Halloween right now when you're watching this video, but at some point when I made this PowerPoint, it was Halloween-ish, like it was the day of or the day before Halloween, so I said, let's get in the spirit. So here we go, a Halloween polynomials. Now we're going to talk about real zeros of polynomials today, as well as the intermediate value theorem, and the whole thing is nice and Halloween colored. Not really themed, it's just colored. All right, so how do we find the real zeros of a polynomial? What we're talking about here is now we have given you this big, fully foiled, right, fully multiplied out polynomial, and we want to know what are the zeros. Where does this cross the x-axis? So we figure out all the possible rational ones. There is a theorem that says the rational roots of any polynomial will be factors of the constant term, right, the no x term, divided by factors of the leading coefficient, right? The highest power of x has a coefficient, that's the leading coefficient. And so the factors of that divided into the factors of the constant term will be the possible rational zeros. If it's a rational number, it'll be something from those. So we take all the factors of the constant, divide each of those by each of the factors of the leading coefficient, put a plus or minus in front of all of them, and make those our possible rational zeros. These are the ones that are possible to test. It doesn't mean they're all going to be true, right? If it's a fourth degree polynomial, how many zeros can it have at most? 4. So it doesn't mean that they're all going to be there, because we could have, 30 different possibilities or more. So how do we know what we're testing? Well, then our next thing is to use some sort of graphing calculator to graph the function and determine where it might cross the x-axis, and pick the possible zeros to test. If it looks like it crosses around 2/3, but 2/3 isn't a possible rational zero, don't test that. Now, you won't always have a graphing calculator on this, and you might have to do this by hand. So my best option is start with the stuff closest to 0. Is 1 or -1 a possible zero? Is 2 or -2? Or maybe we'll do with 3/2 or 1/2. Those are possible ones, right? So start with some of those smaller ones, and you'll eventually get to smaller polynomials that'll be easier to deal with if you can't have graphed it first. Obviously, we'd like to be able to graph it first, and when you're working on this, you'll have a computer or calculator right near you, you can graph it, but on an exam, you probably won't. And so know what your rational zeros are, because something of those is going to work. And then start with some of the nicer, smaller whole numbers. That'd be where I'd say to start. But definitely also try one that has that leading coefficient in the denominator. Like if it's 3x to the 4th in the front, you should try something that's a third, right? Like 1/3 or 2/3 or whatever, because that's going to also matter. But you can also leave it to the end, find all the other ones, and then that'll end up being the last one. So you've got options, and we are going to practice this. But our first thing is to figure out what our possible rational zeros are, and then figure out what to start testing, and then test zeros until all the x-intercepts are found. We're going to do this using synthetic division, but you could also use long division. So here's our first example. Find all real zeros of f of x and use those zeros to factor it. So we have this big 4th degree polynomial, 2x to the 4th plus 11x cubed minus 5x squared minus 43x plus 35, if I could read. And we're going to figure out first, what are the possible rational zeros? What are the factors of 35? 1 and 35. 2 doesn't go into it, 3 doesn't go into it, 5 does. 5 and 7. Any other factors? None that I can think of. Possible factors of 2. 1 and 2. So now possible rational zeros are going to be plus or minus each of these. 1 over 1, 1 over 2, 35 over 1, 35 over 2, 5 over 1, 5 over 2, 7 over 1, and 7 over 2. So there's our possible rational zeros, and it can be the positive or the negative of any of these. So Step 2 is to start testing. So let's try positive 1. Let's see if that works. 1. Now, synthetic division, we put in the number we want to divide by goes into the little box. Next to it, we're going to write all of the coefficients of every power of x from the highest down. So if we didn't have an x squared term here, we would have a 2, and then an 11, and then a 0, and then a 43 and 35. We have to have those placeholders. Just like when we were doing long division with our oblique asymptotes, we needed those placeholders. We still do here too, because this is synthetic division. Any kind of division needs those placeholders. So I'm going to put in my 2, my 11, my negative 5, negative 43, and 35. And let's see if this works. Let's see, 2, 1 times 2 is 2. Now, with synthetic division, we bring the first number down. We multiply the number in the box by the number we brought down, 1 times 2. We put it in the next space, and then we add. So 11 plus 2, that's 13. 1 times 13 is 13. 13 minus 5, so a negative 5 plus 13 is 8. 1 times 8 is 8. Negative 43 plus 8, I believe, is a negative 35. Negative 35 times 1, this worked. I did this on accident. I didn't mean for that to work. Whoops. Okay, so it worked. So this is good. This is where we want to be. That means 1 is a 0. That worked out well. Now we're going to need to try something else. Let's try 5. Now, we can continue here right next to it, right? I don't have to move on to another space. I can just come back to this. And right below it, okay, let's see, 2. And then 2 times 5 is 10. Add 13, now we're at 23. Times 5 is 100 some. We are definitely, this is not going to work, right? Okay. I'm going to erase. You can just cross it out if you have the space. I'm going to run out of space on the screen if I don't erase. So I'm going to take that out. That didn't work. 5 didn't work. Maybe negative 5 would work? Let's try. 2 times negative 5 is negative 10. 13 minus 10 is 3. Times negative 5 is negative 15. Ooh, this is starting to look better. Negative 7. Negative 7 times negative 5 is 35. Works out to 0. So that worked out. That one became nice. My leftover was 0 when I was done. That's the goal. Okay, so far we know 1 and negative 5 are zeros. Now we have a quadratic, right? So this works out to show us that x minus 1 is a factor, and then we would be left with 2x cubed plus 13x squared plus 8x minus 35, right? That's what that row gives us. We factored it once. Then when we use the negative 5, we factored it again. So this next row is telling me that I have x minus 1 times x plus 5 times what's left, 2x squared plus 3x minus 7. Now, you can continue your synthetic division here, or you can factor that. This doesn't factor. So none of our other nice roots are going to be the right ones. So we'll use the quadratic formula for this. So we'll come up here. Negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. This is going to equal negative 3 plus or minus the square root of, let's see, 9 minus 4 times 2 times negative 7, 65. So my zeros, I'll change colors here so you can tell that I'm finalizing this. My zeros are 1, negative 5, and negative 3 plus or minus the square root of 65 over 6. In my factoring, it says, and use those zeros to factor it. This is my final factorization. We're going to talk about a theorem in just a minute that tells us that every polynomial can be factored into a series of linear factors like x minus 1 and irreducible quadratics like 2x squared plus 3x minus 7. It has zeros, but they're not nice, and so we can't factor it, right? So that's why it's called irreducible. So we've done that. We've got our two answers. We've got our zeros and our factoring. So what's next? Find all real zeros of this equation, 4x to the fourth plus 15x squared minus 4. All right. So with this one, we're definitely missing pieces, right? We don't have an x cubed term, we don't have an x term, so when we do our synthetic division, that's going to matter. Let's see what the possible zeros are. We've got, the factors of 4 are 1, 2, and 4. So we've got 1, 2, and 4 for both. So the possible zeros are the plus or minus of 1 over 1, 1 over 2, and 1 over 4, 2 over 1, 2 over 2, which is 1, we can reduce that, that's fine, 2 over 4, which is a half, also already on our list, 4 over 1, 4 over 2, which is 2, and 4 over 4, which is 1. So we've got all of them now. We've got all of our possible solutions, so I guess 10 of them, the plus or minus of 1, or 1 half, or 1/4, or 2, or 4. So we just start. If you can't graph it, right, we can't always graph it, so that's why I'm doing these without looking at the graph first. But we have ideas that we know it's going to be kind of W-shaped, maybe U-shaped, depending. So I'm expecting to have two rational roots here. So let's try 1 and see what happens. If we put 1 in, we've got 4, and then a 0, and then a 15, and then a 0, and then a negative 4. So we bring the 4 down. We've got the 4 times 1 is 4. 1 times 4 is 4. 19, 19, 19, 19, 15. That's not 0. Not ideal, right? So we're going to cross that out. Say, okay, we didn't just do that. That didn't work. 1 doesn't work. So let's try... Do you feel like we need a negative? Let's try a negative. Let's try negative 2. Bring the 4 down. 4 times negative 2, negative 8. Negative 8 times negative 2 is, oops, sorry. There we are at. Negative 2 times negative 8 is 16. All right, this didn't work out quite right? So this is going to give me 31, negative 62. There's no way we're getting back to negative 4, right? Okay, so we'll go back. Negative 2 also didn't work. Let's try something small. These big numbers have been getting just bigger and bigger. That hasn't been helping us. So let's try like 1/2. I went up first, yeah, that didn't work. So now let's go down. Let's try those fractions. So we've got the 4 times 1/2 is 2. Bring the 2 down. 2 times 1/2 is 1. 15 plus 1 is 16. All right, 16 times 1/2 is 8. If I could do math, it's 8. 0 plus 8 is 8. 8 times 1/2 is 4. And negative 4 plus 4 is 0. We found one that worked! That's so exciting. Okay, so now we know that 1/2 is a possible 0. Anybody want to try negative 1/2? It feels like this might be symmetric, right? If we go back from way back, to chapter 1, we were talking about symmetric. We said if it's symmetric to the y, if you sub in a negative for x and you simplify, you get back to the original. That's going to happen with, so let's try negative 1/2. We can use the symmetry to our advantage. Okay, negative 1/2 in here. Bring the 4 down. 4 times negative 1/2 is negative 2. 0. 0. 16 times negative a half is negative 8. That also gives me a 0. So negative a half worked too. So all the real solutions of this equation is really just asking for what are the zeros. So x equals 1/2 and negative 1/2. Those have both worked. Hooray! Now I have 4x squared plus 16. Where does that equal 0? I've gotten down to a quadratic. I can stop using all that synthetic division if I want to. I can get down to here, but here's the thing. I'm going to subtract the 16 over and divide by 4, right? I'm going to get x squared equals negative 4. That's not going to give me any real solutions, and this is asking for real solutions. The next video is where we get to talk about complex numbers and I. So we'll skip past that and say, okay, no real solutions. To this equation, right? So these are my only real solutions to our original equation. Okay, that wasn't too bad. That's what we're going to keep doing. Now, if you have a device with you that you can use your calculator to graph and figure out what ones you should check, great. Otherwise, just guess and check. It's okay to take up a ton of space to do that. It's okay to erase it when you're done. Whatever you need to do. But definitely write them out so that you don't retry them in case you get lost. All right, what else? The intermediate value theorem. I don't always spend a whole lot of time on the intermediate value theorem, but I learned that in calculus, especially AP calculus, there are some specific theorems that we need to know how to use. So we're going to practice with the intermediate value theorem. This doesn't happen to be one of the ones from calculus, which is why we're covering it, but knowing how to use a theorem and how to reference that is really helpful. So we're going to first let our function be continuous and let a be less than b. Okay, so a is lower on the x-axis than b is, and f is a nice smooth curve, or at least if it's not smooth, it's at least, not jumping. Okay. If f of a and f of b are of opposite sign, right? So if you sub in a and you get a positive and you sub in b and you get a negative, or vice versa, then the function has at least one zero between a and b. Now this is kind of important, right? This is actually how we find some of those awful roots, those gross ones, right? We can just keep subbing in an a and a b that are closer and closer and closer together until we find or can approximate to enough decimal places the zero of the function. So we're going to use this, we're going to say, okay, f is continuous, right? Because if it's a polynomial, we know it's continuous. There's no jumps, there's no asymptotes or anything. And you're going to show that a is less than b, your endpoints, one is lower than the other. And then you're going to sub in. You sub in a for x and get a y value. Then you sub in b for x and get another y value. And you'll show that they are opposite sign. Then you can say, therefore, by the intermediate value theorem, there is a zero between a and b. All right. So let's put that into practice. Use the intermediate value theorem to show that the function has a zero in the given interval, then approximate it with your calculator. This would be something that would not show up in an exam where it's saying approximate with your calculator, because you couldn't without a test, without your handy-dandy calculator. But we need to know how to do this, because on the AP exam, you definitely will need to be able to do stuff like this with your calculator. So let's practice it. We are told that our interval is -1 to 0. So we're going to use the intermediate value theorem. We have to meet the conditions, right? F is continuous because f is a polynomial, and -1 is less than 0. F of -1 if we sub it in, I get 1 minus 8 minus 1 plus 2, which is -6. And if I sub in 0, I get 2. So we would then say, because f of negative 1 is less than 0, and f of 0 is greater than 0, therefore, have you guys ever seen the triangle therefore before? Using it here. Therefore, by the intermediate value theorem, there is a 0 of f on the interval negative 1 to 0. Now you do have to write all of this out. I know that you could just grab your calculator and find it, right? That's not the goal. The goal is that you can reference the theorem itself to be able to use that for the function. So it also does say approximate that 0 with your calculator. So let's walk through that. Grab your calculator if you have it. Pause it here if you need to. All right. So we're first going to go to our y equals, top left of your calculator. And we're going to type in our function, x to the 4th plus 8x to the 3rd minus x squared plus 2. Okay, type that into my y equals. Then I'm going to zoom number 6 because I never know what I've been graphing before because of stats. So I zoom 6 so that I can see what I'm looking for. And now I can see, you won't be able to, but now I can see that there's a 0 between negative 1 and 0. So I'm going to hit second and then trace. That brings up the calculate menu. Trace is the button right next to graph. And I want 0. I want to find the 0 on this interval. So now here's the thing. The nicest part about this theorem is that if you're then asked to approximate it, you can type in left bound is negative 1. That's my lower number on my interval that I was given. I'm going to use that negative 1. And my upper bound is 0. And then it wants a guess. So now I'm going to scroll over till I get to my closest point and then press enter. And I get my 0 is x equals negative 0.6046-ish. There we go. So negative 0.6046 is my 0, right? That's the approximate location of that 0 on that interval. Okay. Now, 2 more theorems. We're going to let f be a polynomial. If f of x is divided by the quantity x minus c, right, that linear factor, then the remainder is f of c. What is nice about that is we can turn that around and say, okay, if x minus c, this linear quantity, is a factor, then f of c equals 0. And that means then that if I want to know if this 0 is a 0, if this x value is a 0 of the function, I can sub it in. And if it is, then I can divide by x minus c. Or if I've already done the division, then my remainder is whatever that division would have been. So these are some nice fast ways, especially because we don't always want to do synthetic division. What if you had an equation or a function that was f of x equals x to the 15th minus 4x plus 2, and we wanted to know if 1 was a factor? We don't want to do synthetic division with that because you have to have your x to the 15th and then a bunch of zeros. Ew, right? Like, that's not going to be a whole lot of fun. So instead, we sub it in. We just put a negative 1 there, and if it comes out as 0, great. And if it doesn't, then it's not a factor, and we didn't have to do all that long division in the first place. So that's the nice piece. Okay. Make sure that whatever you sub in, like whatever you put in the little box for your synthetic division, you swap that sign when you put it in as a factor. So if -2 is what worked in synthetic division, then x plus 2 is the factor, right? We swap the sign because x loves to be opposite. Be careful with adding during synthetic division, right? Make sure that you're adding properly. It's a really easy thing to mess up. You watched me do it at least once. So you bring down the first number, multiply, and then add. I know that feels awkward, especially because with long division we subtract. But remember, in long division, we don't swap the sign. In synthetic division, we're swapping the sign, right? We're using the actual 0 up there rather than the factor, which would be like if -2 is our 0, we're using x plus 2 in long division. So that's why in long division we subtract, but in synthetic division we can just add, which is really nice. And then now you're going to come across problems where I will say, hey, sketch the graph of this polynomial, but I won't give it to you in factored form anymore. You're going to have to find the zeros, use those, maybe have some multiplicity with those. So recognize that it's possible for you to use synthetic division. If there's a multiplicity of like 2 for one of those roots, you can use that twice and synthetic divide by it twice just to see if it's a double root. And follow the normal steps, right? So now I would be asking you to put those two things together. Figure out what the zeros are using your synthetic division, right? Using this section. And then finish the graphing by figuring out multiplicity. Where's your y-intercept? What's the end behavior? And then sketching the graph from there. So get ready for some more of this, but with imaginary numbers next.